Okay, hello, this is Dr. Muhammad, and this is another video under the design of steel structures according to AISC. And today we are going to talk about the second part of the compression members. So it is going to be part number 2. And the main contents of today's video is going to be, the main contents are going to be dedicated to the tables for compression members. I'm going to talk about the table 422 in part 4 of the manual, which is considered to be one of the most important tables for the design of compression members. On top of that, I'm going to talk about the available strength tables, or commonly we call it column load tables. And after that, I'm going to give two examples, a couple of examples, and then I'm going to wrap up with some notes about AISC tables in general. Okay, let's jump into the tables directly and see how we can understand it in general and how we can use it in our design. Okay, first of all, we have like two main types of tables. You are going to find them in AISC. The first one is table, we call it table 4-22, which is going to be in part 4 as we have mentioned before in the manual. And you are going to find this table is for compression members whose strength is governed by flexural buckling. Okay, that is not local buckling. If you remember, like a couple videos before, I was talking about the flexural buckling and the other local buckling. Whenever that we have a system or we have column, for example, and this column is connected with a beam. So if this column is going to buckle under the loads coming from the girder or the beam, if it's going to buckle, then a total cross-section is going to buckle in this way, for example, and we call this as flexural buckling. This is flexural failure, mode failure. But if there is certain part in the section that is going to be buckle, for example, if we have this is the cross-section of the column, for example, if the flange or the beam, or the web is going to buckle locally, then in this case, we call it a local buckling failure, and the system or this cross-section is going to be slender. So it will be having another type of or another procedure in order to design this type of members. So we are talking about flexural buckling, that is not local buckling at all. And table 4-22 in part 4 of the manual, which is titled with design of compression members, can be used in this case. Okay, this is only one note regarding this table that we are going to look to it in a while. This table gives values of phi c FCR for load and resistance factor design, and FCR over omega c for the allowable stress design as function of KLR for various values of F yield. Okay, so we're going to find, this is the table 4-22. We're going to find it in part 4 as we said in the manual. You can stop the video now and you can browse your manual and go to this part, which is part 4, and you're going to find this table, which is table 4-22, titled with available critical stress for compression members. Okay, and if you are going to look to it, you are going to find that different yield strengths given to you, as you can see here, and you are going to find that every column is divided into two parts. Okay, divided into two sub-columns. The first one is related to ASD, and the second one is related to LRFD. Okay, so this is what you are going to find. So under each or under every yield strengths, there are two different columns. Every one of them is providing information for LRFD and ASD, which is the available or the strength, the allowable strength, and the design strength for LRFD. Okay. The last thing that we want to highlight is regarding this table, it is related to KL over R for various values of F yield. This means that if you look to the most left column here, you're going to find that it is KL over R, KL over R, right? The slenderness ratio, and starts from 1 and goes until that it is going to reach, here it is 120, but it's supposedly at the end it should reach 200. And in this case, we are going to find that this table is very useful whenever that we are going to look to or show the strength or the flexural buckling strength of the element, okay, knowing its KL over R, the effective or the slenderness ratio. Okay, so we're going to find that this is here in this column, in the first column. Okay, and the last thing, this table stops at recommended upper limit of KL over R, as I said before, 200. This is our limit here. So you are supposedly to find, if you go and browse your manual, you can check it right now. The last value here, or the bottom here, or the flooring of this column is going to be 200 as our limit. Okay, so this is the first type, which is table 4-22. And these are the most important points that you need to keep in your mind. Okay, another type of table or tables, we call it available strengths tables, and we call it column load tables. Okay, column load tables. This available strengths tables, however, are the most useful. So if we are going to compare, and from the practical standpoint as well, you're going to find that you are going to check first column load tables even in your design, and after that you're going to check the 4-22 tables, okay, which means that this is the most useful for you and most practical as well. These tables, which we'll refer to as column load tables, okay, it provides, or these tables, they provide the available strengths of selected shapes, both, which is phi c Pn nominal strength times the strength reduction factor, this is for LRFD, or the allowable strength Pn over the omega c for ASD, as a function of the effective length. So here, this table, we are using KL, remember that well. However, for the table 4-22, we are using KL over R. So remember well, KL over R, which is the slenderness ratio. Here we are dealing with the effective length. The effective length. Yes, it is going to be related also to the minimum radius of gyration, but again, the table itself is going to be like highlighted, or the title of the column, the first column, is going to be titled with the KL. So this is an example of the available strengths table. We call it column load tables. So you can browse, you can stop the video now and go to your manual and open this 4-1 table. This is for wide flanged shapes, for example, and for F yield equal to 50, you're going to find that the tables are provided, and you're going to find that in the left column is going to be, we're going to give to you the effective length with respect to the minimum radius of gyration, which is Ry, because we are like taking, this is X, and here this is Y. So whenever that we are talking about R minimum, this means that we are talking about exactly Ry. Okay, the radius of gyration, the minimum radius of gyration is related to Ry, not Rx. Okay, so remember that well, because we are going to like modify it whenever that we are going to check for buckling around X, for example. Okay. Okay, anyway, the table, as you can see here, It is titled with available strengths in axial compression in kips. Take care, we are using these units, kips. Okay, and you're going to find in the top row it is the this is white flange, for example, 14. It is the dimension of it, the height, and then the weight per unit length, which is going to be given in the second row, as you can see. And after that, the third row is the design, giving to us two rows. First, it is giving only ASD and LRFD, which is designated, as we know, with PN over omega or phi C times PN. And then they are like two columns, as you can see here. These two columns, every column is providing for us the available strengths in axial compression for the corresponding KL or effective length with respect to the minimum or the least radius of duration. Okay, so if we go to a specific value here, we're going to find that it is going to give for us the values required, the available strengths in axial compression, whether for ASD or for LRFD. Okay, and you're going to find that something interesting in the table, that you're going to find like a thick line here, and then there is nothing here, it is white area. This means that this shape stopped here because, as we said, we have a limit which is KL over R should equal to 200. So this is the corresponding of KL over R equal to 200. Even that here we are using KL, but the correspondence with KL over R equal to 200 is going to stop here. This shape cannot go for this KL, okay, based on its radius of duration, of course. And also you're going to find in the bottom of this, this table, you're going to find properties, and these properties are like the properties of the cross section itself, giving to us different properties, like the area, for example, which is important property here, and another very important properties or property, which is Rx over Ry, which is the ratio of the radius of gyration Rx over Ry. Always for W shapes, for example, Rx is going to be larger than Ry, then it is going to be larger than 1, as you can see here for all sections. Okay, so this is like the shape of our table. Again, we are the table, or these tables include values KL up to those corresponding to KL over R equal to 200. Okay, and these tables, they are the tables, they are from 4-1 to 4-20. You are going to find all the tables, many cross sections there, the wide flange and different types and shapes based on the number of the table. Okay, so this is, as I said, you are going to find it is given to you under the title of the table. It is going to give to you the type of the shape. Here it is wide flanges. Okay. Okay, so now to conclude this, we have, as I said, we have two main tables for the tables for compression members. Like broadly we can say, like table 4-22, and we need to go through it by KL over R. The other one is like from 4-1, if we're talking about the wide flange, for example, till let's assume 4-20. These are the tables, okay, we call it column load tables, and we are going to use KL here. Okay, so this is KL over R. Here we are going to use the KL, or the effective length. As I said, from the practical standpoint, commonly we are going to use the column load table first. Okay, however, 4-22 is going to be available for us to use, and we are going to use it, okay, from time to time. Okay. Okay, now let's go to the next point, which is related to some few hints about this table, which is table 4-1. especially when we are talking about this effective length, because really it is a little bit confusing for some people that if we are going to check around XX, for example, so it is sometimes we enter this, or some people they are entering this with the RX, for example, which is not right in this case. We need to give an equivalent radius of gyration in order to enter to this table. Okay, so we need to calculate a kind of equivalent radius of gyration. So here the point is let's read this part because it's important in the manual. Available strengths in axial compression are given for wide flange shapes with F field equal to 50 KSI according to STM. Okay, the tabulated values are given for the effective length. It is given for the effective length, as we said, with respect to y-axis, y-axis. Okay, we are talking about this is x and this is y here. Okay, so we are talking about KL with respect to y. However, the effective length with respect to x-axis, which is the horizontal one, which is KLX, we call it KL with respect to x, must also be investigated. To determine the available strengths in axial compression, the table should be entered at the larger of KL with respect to y and KL with respect to y equivalent. Okay, take care. This is related to KL with respect to y, and we are going to calculate something related to KL with respect to x, which we call it KL y equivalent. Okay, that's it. This is how we are going to use the table. Okay, so in this case, how we can obtain this KL y equivalent. Okay, so we are going to say that KL x, which already we have, it is going to be divided by the ratio that is, which is Rx over Ry. Okay, Rx over Ry. Where we can obtain this ratio, okay, these values for the ratio Rx over Ry and other properties useful in the design of wide shape or the wide flange shape compression members are listed in the bottom of the table 4-1. Let's go here. This is the part that I'm going, that already I have like mentioned or indicated, and this is Rx over Ry. This is Rx over Ry, and you can read it from here. Okay, so the table, these tables are important in terms that they are providing properties important for you while solving the problem itself or the example. Okay, so remember that we need to check both in your design, KL with respect to y and KL with respect to x, but for KL with respect to x you need to calculate what we call it the equivalent KLY equivalent, which is going to equal KL with respect to x over the ratio Rx over Ry. Okay, I hope that we can understand now. I think that we are ready now for going forward. This is only like zoomed in picture on the table. This is the properties. As we said, you're going to find a lot of things here. The most two important things I think that maybe you are going to use from time to time is the area, gross, and this ratio, which is Rx over Ry. You're going to find, as I said, it is always larger than 1 because we are talking about this this element, which is having Ix or the radius of gyration around x is going to be always larger than radius of gyration around y. Okay, and at the bottom you are going to find some notes. One of them, this is heavy line indicates KL over R equal to or greater than 200. This is what I have mentioned before. This is the thick line here, okay, which is corresponding to KL over R equal to 200. It's our limit. Okay, it's our limit. Okay, now let's go and jump into another part, which is we are ready now, I think, for taking the example number 1. Okay, in this example, we are going to compute the available strength of the compression member of example 4.2 with the aid of table 4-22 and the column load tables, okay, which is table 4-1. So we have here like two different ways that we need you to go through in order to design. Okay, so first of all we're going to use the 4-22, and we need to know what is the example 4.2, because we need to know what are the length, for example, and K of the member. So let's go here. This is the example 4.2, which is giving to us the dimension or the cross section, the shape that is going to be used, which is wide flange 14 by 74, and it is A 99.2, which means that F yield equal to 50, and steel, and has a length of, this is the length here, which is needed for us to calculate KL over R, and pinned ends. Pinned ends means that we are having K equal to 1. So these are the information provided in the previous example. We have wide flange 14 by 74. This would give us information about the element. F yield is going to be 50 KSI, because we are talking about this type of steel, A 99.2, and K, or the length, is 20 foot, okay, and K equal to 1 because we have pin ends. So these are the most important information for us we need from this equation, or from this example. Compressive strength for LRFD and the allowable compressive strength for ASD, this was required in the previous example. Okay, so now the KL over R for this element, we are going to find it, because we need to always get the maximum KL over R, okay, to compare it with 200. This is our limit. So K, which is 1 times 20, which is the length in foot, times 12, which is the conversion from foot to inch, and then over 2.48 RY. From where we can get this RY? You can stop the video and go to the tables of dimension and properties table for this cross section, and you are going to find 2.48 for the radius of gyration, RY. Okay, and you can find them, because in the beginning you can find it if it's provided for you in the table here. If you can find it in the table here, you can get it. I mean that it is available from different sources. Okay, so you can obtain it from the dimension and properties table. Okay, one of the sources. Then this KL over R, the maximum is 96.77, which is less than 200. Okay, this means that it is okay. Anyway, we are going to use this piece of information, or this value here, KL over R, for our design. Okay, let's go back again. So now we know everything about our element. Okay, let's start with the LRFD, and we are going to use, as we said, two different approaches, one of table 4.22 and the other 4-1. From the previous example, we said that the maximum KL over R, take care, we are talking here about the maximum. When you calculate, you should calculate R here with the minimum value. Okay, so this is in order to give you the maximum slenderness ratio, okay, as we said before. Then F yield is 50. Values for VCFCR from table 4.22 are given only for integer values of KL over R. Let's check this. If you go to the table 4.22, you're going to find that KL over R, it is given in integers. Okay, 81, 82, and so on between 96. For example, if we're talking about our case it is 96.77, right? So we are here. We are 96.77, between 96 and 97, right? So this means that which one that we are going to take, we are going to have like interpolation, okay? Or we can make a round if you can rounding the one of them, but actually we use here, let's use interpolation. Interpolation is going to be the best way and the most accurate one. So we are going to go to table 422. Please, you can stop the video here and go to your manual and check what I am saying. So going to 422, table 422, and you are going to the F field 50 because we are dealing with the steel A99-2. We are using A99-2. This means that we are F yield equal to 50. And then we're going into this table, which is KL over R, going down until that we reach to the value of KL over R that we have obtained, the maximum one, which is 96.77. Then going here, you're going to find some, we are in between here because this line, the right column, is giving us phi C times FCR. Okay, this is phi C times FCR. This is for LRFD, the strengths, design strengths for us. Okay, and by interpolation, we can find that our value is going to be between the two values here. So, which is going to be taken as 22.67. This is from table 422, okay, as we have said here. So it is here 22, as we said, 0.67. Okay, 22.67. Okay, now this is the design strengths for this, and we are going to use this value in order to get, yes, the design strengths, which is phi C times Pn, and this is going to be phi C times FCR, which we have already obtained it from the table, times the area gross. Okay, as I said, area gross can be obtained from the dimension and properties table, or you're going to find it from the 4-1 table. You can find it here, okay, which is 21.8. This is from the bottom of table 4-1, or from the dimension and properties table. Okay, that's both of them are okay. Okay, so now this gives to us how we are going to calculate. Okay, so we obtain the value from the table and then multiply by the area gross to obtain the design strength. Okay, the design strength is 494. 494. Okay, now this is the load, that is the available load after obtaining it from the table. Let's go to the second point, which is using column load tables. We're going to obtain this value directly here. The column load tables, which is 4-1 in part 4 of the manual, give strengths for selected, okay, it's not for all shapes, it is for selected shapes. Wide flange, HP, single angle, the wide flange T-shaped, hollow structure sections, pipe, double angle, and composite shapes. Okay, so the tabular values for the symmetrical shapes, like wide flange, HP, HSS, and pipe, were calculated by using the minimum radius of gyration. Take care again. As I said, let's go again and see. We are talking about KL. We're talking about KL with respect to the least radius of gyration. Take care. It is RY in our case. Okay, so in this case, we are going to get KL, which is 1 times 20 foot. Then we are going into the table. So now we can stop the video and visit the table on in your manual. So at 20, this is for the design, and this is KL with respect to RY, it is 20 here. Then we are going to, this is F field 50, and then we are having white flange 14, okay, and then we are going to 74. This is the weight per foot or per unit length, and then we have ASD and LRFD. So we have LRFD here, which is 494. So you go F field W14 and then 96, and then you can obtain the value directly here. Okay, this is why the like the available strengths axial compression tables, okay, it is like easier because we do not calculate anything, just we go like this here in the table and then we can obtain it directly. Okay, it's like saving us one step if we are going to compare it with the 4-22 table. That's it. Okay, so in this case for our W14 by 74, this is the weight, this is the dimension or the height, and then F field 50, as we said, KL 20. These are the information that needed for entering the table. Okay, after that you can obtain the VC PN easily as we have obtained it here. Okay, just you go to exactly the values that you are having for your cross section and then it will be okay for you. Okay, so now this is the like LRFD. We're talking about LRFD. Now let's jump into the other solution, which is ASD. Okay, the ASD solution. You are going to find it also very very simple and straightforward as we have explained for the LRFD. Again, A and B, we are going to use table 4-22 here, and we are going to use table 4-1 here, okay, in A and B. So from the example, again, we have KL over R. Take care that we are using here KL over R. It is 96, F field 50 as we said. By interpolation for KL over R, we're going to obtain the value for us. It is 15 something. Let's go to this table and see how we can get this. It is also the same as we have done before. This is the same table that as we have done in LRFD. Then this is KL over R, we know it. It is 96 point something as we said. Then we are going to value of F field equal to 50, and then instead of LRFD we're going to ASD. Then you're going to find two values here, 15.3 and 15.0. Then we're going to take the, by interpolation we can obtain the value in between. Okay, so this is what we have obtained it here. It is 15.07 KSI. This is from the table 4-22. Okay, note that this is the allowable stress. This is, as we said, allowable stress. It provides for us FCR over omega C. This is allowable stress. However, if we want the allowable strength, which means that force here, this value, it is stress. Okay, this value is stress. If we want to get the strength, then we need to multiply by the gross area. So we need to say that Pn, the nominal strength over the safety factor or omega C, equal to FA, which is the allowable stress that we have obtained, which is like equivalent to 0.6 FCR, times the area gross, which is 21.8. From where we can obtain this? Exactly from the dimension and properties table. Please stop the video and go and check it, or you can obtain it easily from the 4-1 table as we mentioned before. You're going to find it here. This is the area gross, and you are going to find the value, which is 21.8. Okay, when we multiply FA by AG, it gives us 329 kips. Okay, this is the allowable strength based on ASD using table 4-22. Okay, you're going to find that we have like obtained the value from the table and then multiply by the area gross, like 2 steps here. But here, when we are going to use table 4-1, we're going to find that directly we are going to obtain the value from the table by entering the table with K times L. K, it is 1 because we said that it is pen column. So K equal to 1 and KL equal to 1 times 20, which is the length of the column. This means that 20 foot. Then from the column load tables, table 4-1 for the wide flange W14, then the weight is 74. Okay, this is per unit length with F yield 50. Please stop the video here and go and check the table again. You're going to find it as we have explained it before, but it is very important for you in order to get familiar with the tables to go and use it by yourself. Okay, and for KL, so these are the information needed. W14, the weight per unit length, F yield, KL. These are the information that we need. Then you are going to find from our table here. Yes, this is F yield. Okay, take care, we're talking about table 4-1, browse in it, and then for F yield 50, then for W14 times 74, then we are talking about ASD. So go to ASD, where that our KL, we're talking about KL here, 20. So we are here. Yes, you're going to find it 329. 329 as we have obtained it before. Okay, 329. Okay, so this is, yes, here 329 directly. Okay, now this explains to you in a very effective way the difference between the two ways for us to design the column. It's not the design, only to use the tables. That's it. This is the main reason for what we are doing here. This, we are like having table 4-22 here, and we are having table 4-1 here, and we said that commonly it is easier to use this table 4-1 because it's directly would give to you the design strengths if we are talking about LRFD, or the allowable strengths if we're talking about ASD. And these like this example, it would provide you with like insight how to use the tables in general for the column design, which is going to be taken in the next video. Okay, the last thing that I want to highlight here for the tables is some notes, like few notes, like 3 notes here I'm going to share with you regarding the AISC tables. It's important to keep in our minds when we are using them. Okay, first of all, the values from table 4-22 are based on flexural buckling. It is based on flexural buckling. And AISC equation E3-2 and E3-3. Remember well, these are the two equations that we have spent a lot of time explaining them last time, right? So this means that the AISC is like saving us the time by computing for us the available strength for the sections based on one failure mode, which is flexure buckling, okay? And it uses these two equations, whether elastic or inelastic buckling that is going to take place. So what is the meaning of this? Why it is important here? Because local stability is assumed. That's important, that whenever we are checking our column, for example, we are not expecting that the flanges or the web to buckle or to have any kind of local stability issues. Okay, so local stability is assumed to be safeguarded, or it is going to be, local stability is fulfilled. Okay, and width thickness ratio limits must not be exceeded. Okay, so we need to take care of this. that the width to thickness ratio limits must not be exceeded in this case. Okay. Another hint, which is important also, although some shapes in column load tables, we are talking about the column load tables now, it is 4-1, exceed those limits, that is the limits that we were talking about, okay, the limits of the flange and beam, which is the width to thickness if we're talking about the flange, or height to thickness when we are talking about whips. So in column load tables, okay, some shapes, they are exceeding these limits, and they are identified with a C footnote, which is like an indication that this cross-section is having some problem regarding local stability for one of its elements, like the flange or web or so. So the tabulated strength has been computed according to the requirements of AISC section E7, which is members with slender elements, and no further reduction as needed. So this is very important hint. Okay, so we need to confess that there are some shapes in column load tables exceed those limits, the limits which is I mentioned here, okay, for the local stability issues. Those sections, they are going to be identified with C footnote. The tabulated strength has been computed according to the requirements of AISC section E7, which is related to slender members with slender elements, and no further reduction is needed. Already the strength is reduced in order to take into account the local stability issues. Okay. So this is the main one of the biggest difference between, like, we are talking about table 4.22 here, and we are talking about table 4-1 here. We're going to find this C footnote on several shapes. Okay, and the last thing, I think that the last hint, I have mentioned about it before. From a practical standpoint, if a compression member to be analyzed, if we're talking about analysis, to be analyzed can be found in the column load tables, then these tables should be used because it's easier, as we have seen before. Otherwise, table 4-22 can be used for the flexural buckling strength. Okay, so we have like these two alternatives: start with column load tables, or after that, okay, then these tables should be used. Otherwise, if you couldn't, then in this case you can use table 4-22 for flexural buckling strength. Take care, flexural buckling strength. There is no local stability issues here, as we have mentioned in the first hint. Okay, so if the member has slender elements, the local buckling strength must be computed using provisions of ASIC E7 or AISC E7. Okay, what we want to go and summarize these hints. It's important here to say that. So if we have, yes, this is before going and explaining or summarize these hints, this is the footnote that we usually can see at the end of the table. Okay, which is here, this is C. You're going to find C something like this, and they said that shape is slender for compression with F field equal to 50. So under this 50, you're going to find that some shapes, they are highlighted with the C, as I'm going to show to you maybe later in the next video. This means that it is like we are talking about table 4-1 here, so this means that the available strength is already computed based on taking into consideration the slenderness effect. Okay, so what I want to say here, like 4-22, it is only based on elements that for flexural strength only, available flexural strength, available flexural strength. This is the point. no local stability issues. Okay, this is very important. Okay, this means that we are using this table if we are going to, or we are sure that our cross-section is going to be stable locally or have local stability. Okay, if our section is having some other issues, okay, which is local stability issues, in this case we need to reduce whatever that we obtain from this table. We need to reduce it based on E-7 chapter in ASIC. Okay, that's very nice. That's fine. For table 4-1, okay, table 4-1, everything is taken there. Everything is taken. So you're going to find that the slenderness issue is taken into consideration. Okay, so local stability issues for some shapes are taken into consideration. Local stability issues are taken into consideration. Okay, how we can know this? You're going to find that C footnote at the bottom of the table, and the shape is going to be designated with C, for example. This means that it is reduced for slenderness or local stability issues. Okay, this is major difference between the two. Please remember that very well. Remember that very well. Okay. As I said, this is going to be flexural buckling only for table 4-22 and ASIC equation. This is like elastic and inelastic, and thus local stability is assumed, means that it's maintained, and width thickness ratio limits must not exceed it. Otherwise, you are going to reduce whatever that you obtain from here, from this table. You need to reduce it if the shape is slender. For table 4-1, okay, or the column load tables, okay, if the limits are exceeded, okay, and they are identified, they are going to be identified with a C footnote. The tabulated strength, that's very important, the tabulated strength has been computed according to the requirements of ASIC section E7. Means that already we have reduced the strength for you to take into consideration the slenderness issues, the local stability issues. Okay, so already it has been designed based on the members with slender elements section or chapter in AISC, and remember, no further reduction is needed. Okay, this is what I want you to remember well, between the difference between 4-22 and 4-1, and the issue regarding the practical standpoint. We always start with column load tables. After that we go to this table if we couldn't use the first table, for example. Okay, so otherwise we use table 4-22 for flexural buckling strengths only, without consideration for the local stability. This brings us to the end of this this video. I hope that you have understood it very well, and I hope that it provided you with the information that is needed for using the tables, and I hope that by the end of this video you have understood the main contents that already we have mentioned in the beginning. Now you are able, after like understanding this video and going with the main steps in this video and using your manual, I'm sure that you are going to be able to use the column tables for compression members, whether it is table 4-22 in part 4 or the available strengths tables, which is, we call it column load tables, efficiently. You know now what is the main difference between the two, when to use this table and when not, and what is the advantage of column load tables over the table 4-22. And then we have worked out together a couple of examples, and then we highlighted the some important notes about these tables. I hope that you have understood this video well, and I hope that after finishing this video, please go to your manual and go through what I have explained, especially for the examples. Go through them using your manual and try to familiarize yourself with using it. That's it for today. Thank you very much, and see you in the next video.